Ok, donc je remercie les organisateurs de m'avoir donné cette chance de vous parler aujourd'hui. Comme vous voyez, donc l'exposé va être en anglais, donc Strange Duality at Level 1 for Anti-invariant Vector Boundaries. Okay, I think most of the audience today is not specialized in algebraic geometry, so I will give an introduction, a highlight of the language of algebraic geometry, and then try to explain to you strange duality theorem, and then trying to explain also the result we are working on right now. Okay, I don't know if my voice is clear like this. Is it okay?
Yes.
Okay, first of all, in algebraic geometry, we are interested in what we call algebraic varieties, which are solutions of system of polynomials of equations. So in a affine or projective space, that's what we call algebraic variety. And maybe the most interesting problems in algebraic geometry are classification problems. What we mean by that, we are looking for some parameter space that parameterize our geometric structure that we are considering. So we want to understand how this structure, for example, algebraic variety special case, how they manage in families, or how they moves in families. And that's the resultant of these, the solutions of these classification problems are what we call moduli spaces. So we are looking to find some parameter space which they are again algebraic varieties and have some properties that allow us to understand more about the geometry of the variety or the geometric structure that we are considering first. So these are the moduli problems or the moduli spaces. For example, if we consider lines in the plane, for example, I give two examples to clarify things here. So if we are considering lines in R2 that passes through the origin, so linear lines, if you wish, then the resultant space is what we call the projective line. I'm sorry for people who are specialized in algebraic geometry because this is so basic. So maybe you can benefit from the second part. But yeah, so if we consider the problem of classification of lines in R2 which pass through the origin, then one notices that given a point in the circle in the origin is the same as that give you, if you have a point in the circle, then you have a line that joins this point with the origin. But you have actually, this gives you a 2-to-1 cover of your parameter space, what we call 2-to-1 morphism. So our parameter space in this case is isomorphic to S1 over the equivalence that identifies P and minus P. And this is the first example. And actually, any projective space is a moduli space for surfaces in the affine space that you consider. So this is a basic example. Another example is given by, for example, the elliptic curves. If you consider smooth projective variety of dimension 1 of genus 1 in complex geometry, this is equivalent to a torus. So you think it's geometrically like a donut, and which is a surface with just one hole. That means the genus equal 1. So elliptic curves are known to have some special type of equation in the form y squared equal to x times x minus 1 times x minus lambda, for lambda different from 0, 1. This is called the Langland form equation that give you an embedding of the elliptic curve inside P2. And this lambda allows you to define what we call the G invariant of the elliptic curves. If you have two elliptic curves with the same G invariant, and they are isomorphic. And so you have a parameter space for isomorphism classes of elliptic curves, which is A1. Okay, so the G invariant classifies all the elliptic curves up to isomorphism. These are two basic, and the solution in this case is complete. But in general, we cannot wish to get something like this. The moduli space that we get in general classifies not just isomorphism classes, but we have to weaken the condition and to consider, for example, other equivalence classes, which are more general, as we will see in a moment in the case of vector bundles. Okay, so in this talk, I should define what means a vector bundle, because the strange duality is defined of the moduli space of vector bundle. So a vector bundle, you can think of it as a fibration by vector spaces. So if you fix a smooth projected complex curve of genus G bigger than or equal to 2 from now on, and a vector bundle over X is a family of vector spaces of dimension R, with the condition that they are locally trivial. You can think of this as, for example, this picture, which gives you a vector bundle, in this case is a line bundle, because it's fibration by lines over the circle. And the total space in this case is, as you see, is the Mobius strip. And it's actually a surface, and you can see it like fibration over a circle, and this gives you an non-trivial line bundle over S1. So in general, fibration by vector spaces of the curve, which is locally trivial, give you a vector, what we call vector bundle. Okay, so we want to understand how vector bundles behave in families. So we want to classify all vector bundles that we have, but this is not possible due to some fact that actually, as we will see, that these family vector bundle is not bounded. So there is no algebraic variety that parameterize all vector bundle, even if you fix the rank and degree. So let me define some basic stuff here. If you have a vector bundle, the space of a global section is the space of morphism from the base curve to vector bundles, such that the image of any point is in the fiber of that point. Okay, so it means that the projection composed with the section gives you the identity on the base curve. That's we call a global section, and we use the notation of homology not XE to denote the space of the vector space of a global sections on E. So, okay, there is another invariant. If you have a vector bundle, then you have a degree of a vector bundle, which is defined as the degree of the top exterior power of E. Okay, so if you take the top exterior power of a vector bundle, then you get a line bundle of E. And to define the degree, I think it's easiest way to see that actually line bundles are in one-to-one correspondence with veiled divisors. Veiled divisors are just a formal summand over Z by points. So if you have a finite formal summand by over Z with coefficient in Z of points in your curve, this is called a veiled divisor, and there is one-to-one correspondence, at least in the smooth case, for any variety actually, between line bundles and veiled divisors. And the degree is defined simply as the summand of the coefficient. Okay, so we have two invariants for any vector bundle here. The rank of the vector bundle, which is the dimension of each fiber, which is equal everywhere, and the degree of the vector bundle. So we hope that that there is a moduli space that parameter vector bundle fixed rank and degree. But even so, this is not possible due to the fact that the family of vector bundle fixed rank and degree is not bounded. And the problem here came from some fact is that if you have a flat family of vector bundle of fixed rank and degree, then the H naught that I defined earlier, the H naught here, the dimension is also bounded. for any family of vector bundle, flat family of vector bundle of fixed rank and degree. So this is not bounded because this H0 we can make it arbitrarily large as we wish, and this is came in from the fact that in a vector bundle you can have a sub bundle of arbitrary large degree, and in somehow the degree tells you how many sections there are. I mean, informally. So this the problem that I mean, this is the problem where we should solve. I mean, if we wish to find a moduli space that parameterizes this vector bundle, we have to make some condition on the sub bundles in order to get some bounded family. So what we mean by bounded here, bounded means that there is an algebraic variety scheme or whatever that parameterizes your family. In some sense, there is a rational map from S to V. I mean, any vector bundle can be put in one-to-one correspondence with some open subset of some algebraic variety. Okay, so to find a good moduli space, we need to make some other condition on vector bundle fixed rank and degree. And these conditions are called semi-stable conditions. And the semi-stable conditions are related to the degrees of subbundles, and they are defined as follows. If E is a semi-stable if for any subbundle f of E, the degree over the rank of f is less or equal to the degree over the rank of E. This is called the slope of f is less or equal to the slope of E. So with that done, so with these all conditions, now we have a result, which is classical result that there exists a moduli space that parameterizes vector bundle of rank R and degree D, which are semi-stable, but actually does not parameterize isomorphism classes, but in general, it parameterizes what we call S equivalence classes of semi-stable vector bundles. This result is due to Mumford and Seshadri and Narasimhan and other. It's I think it's in the 60s where they constructed this moduli space using geometric invariant theory. Okay, so what means S equivalent classes? I don't want to go in details here, technical details, but roughly speaking, it means that there is in the equivalence classes there is some vector bundle which is came in from subbundles which are stable. I didn't said what stable is. Stable is vector bundle E, which verifies this condition, but strictly here. Any subbundle is slope of any subbundle is strictly less than slope of E. Okay, so the S equivalence is larger than the isomorphism classes, but actually in special cases, for example, if R and D are co-prime, then the S equivalence classes is the same as the isomorphism classes, and this is easy fact due to due to the definitions actually. And actually, this moduli space is a smooth projective variety, and this is good. Okay, and in this case also we have a nice structure. This is called a fine moduli space. That means it parameterizes the functor that classifies the moduli functor of the problem. I mean, any family is, or in other words, there is a universal bundle on it. We can easily say that there is a universal bundle. Okay, what is a universal bundle? Is a bundle over the product of the base curve with your moduli space, such that its fiber over any isomorphism classes here in the moduli space is isomorphic to this point itself. Okay, so it's a family of vector bundle parameterized by this moduli space, such that the selection to any point of the moduli space is isomorphic to this point itself. That's what we call universal bundle. Okay, and in the general, this universal bundle doesn't exist if R and D are not contract. Okay, there is another version of moduli problem using moduli stacks, which we can do geometry also on them, and in this case there exists always universal bundle. But in the algebraic, if we look for algebraic varieties, this is the best that we can get. I mean, in this moduli problem. Okay, so I will need also to define another moduli space of vector bundle rank R and fixed determinant, which is a sub-moduli space of this one, which parameterize as equivalence classes of semi-stable vector bundle of a fixed determinant isomorphic to L. Okay, so far so good. Okay, okay. There is another definition which is very important in order to, in our case, which is the determinant of cohomology line bundle. Over this variety that we just saw, the moduli space of rank R vector bundle and degree D, there is line bundle over this moduli space. So it's a line bundle called the determinant of cohomology line bundle, which is defined as the determinant of cohomology of the higher direct image. Okay, so, but there is an easier definition which uses generalized theta function. So we can define this this line bundle as the line bundle associated to the divisor, the Bell divisor, which is a hypersurface in this moduli space defined by vector bundle. This theta function is the subset of the moduli space here, given by this condition that H naught E times F is non-zero, by the mean that this tensor product, this vector bundle, has at least non-zero global section, where F is some fixed vector bundle that gives us some numerical condition that the Euler characteristic is non-zero. So there is an hypersurface, you can think of it like this. There is an hypersurface here, Bell divisor, well-known Bell divisor here, depending on some fixed stuff here, such that the associated line bundle is what we call the determinant line bundle. And what we are looking for is to understand the space of global sections of the power of this D. So the goal is to consider the space of global sections of this line bundle, which is the determinant of cohomology line bundle, for some power D. And okay, so all right, so this is the determinant of cohomology line bundle. So strange duality now is duality, which means an isomorphism between a vector space and the dual of another vector space. And these vector spaces are actually the generalized theta functions vector space, which are global section of power of this determinant line bundle. Okay, so it's really surprising because no one was expecting this duality. It's called strange because it's strange. Okay, yeah, for simplicity, let me take the D equals 0. Okay, so the strange duality says that we have a natural isomorphism between the global let me precise here, between the dual vector space of generalized theta functions of level K over the moduli space of vector bundle of rank R and fixed determinant L, and the vector space of generalized theta functions of level R on the moduli space of rank K. Here you see that in one side we have fixed determinant case, on the other side we have not, but we need to take some degree different from 0 in order things to behave in a natural way. Okay, okay, so you see here we interchange R and the level K. So we interchange R and K and drop this condition on the determinant, we get this space. So it's really strange. Yeah. So okay, what can I say also is okay, this is proved by Berkel, which is Indian mathematician, for general curve in 2006, and also by Marian and Oprah for all smooth curves in the same year. So it's a recent result, and but special cases are already known for rank 2 and rank 1, and the first special case is due to Bobil and Narasimhan and Ramanan in 89. I think they have just this paper, which the only paper between these stars, and yeah, they studied the moduli space of rank R and degree D, and they used the Hitchin system to prove this special case, which also very interesting in our case, because our project is exactly mimicking this situation in some different moduli spaces. So let's see the moduli space of rank 1 and degree 0, which is actually an abelian variety. It's very well known abelian variety. It's classical. It's called the Jacobian variety of X, and it's actually has all the information you need to about X. It's a group. That's what we call abelian varieties. Abelian varieties are algebraic variety with the structure of a group. Okay, this abelian variety we denoted. It's actually also the connected component of the identity of the picker group, X0. I will denote it always by this notation. And I can say also that it has the same dimension as the genus of X. Okay, so if we take the case, also it parameterizes line bundles. Okay, that's I already said. So if we take the level k equal 1 in our strange duality here, if we put at the place of k 1 here, then we get here the moduli space of rank 1 vector bundle. That's the line bundles of degree g-1, which is the picker group of X at the degree g-1. And here we will have the determinant line bundle of the Jacobian, which is the principal polarization, at level R. And the other side, we have rank 1, level 1 theta function, generalized theta function. So we get this duality. So the duality will be between level 1 generalized theta function over the moduli space rank R vector bundles and the classical theta functions of level R. And the proof in this case was given by Bobil, Narasimhan, and Ramanan in the 89s, and they use a very well and very powerful tool, which is the Hitchin system. We call it the Hitchin system. I will explain this Hitchin system in the second part of this talk. But okay, so in our case, we are interested in another moduli space, which is the moduli space of anti-invariant line bundles. Anti-invariant, let me say, vector bundles, not line bundles. But let's start with what are the anti-invariant line bundles. Anti-invariant line bundles are line bundles which are anti-invariant for some involution. Okay, so assume that we have over X an involution, sigma, which is, that means a map of order 2, sigma square equal identity, and denote the quotient curve by Y. So we have a double cover here, which may be ramified at some point. That means sigma here, there is no condition, may have some fixed point. And yeah, so we consider there is an abelian variety classically attached to this setting here called the prime variety, which is sub-abelian variety of the picker group of X. And it is defined as the connected component of the kernel of the norm map. So what is this map? Is okay, the norm map can be defined, and the easiest way maybe to see this map is using the veiled divisors. So if you take here a line bundle, which is you take an isomorphism classes of line bundle here, and you take a representative here, which is a veiled divisor, and then the image of this point will be just the isomorphism classes attached to this veiled divisor here. you just take the image of these points by this double cover. Okay. Okay, you can define it otherwise by partial word, but this is, I think, this is well. Okay, so given a line bundle in P, it verifies this equation. It is, if you pull it back by the involution sigma, then you recover the dual of the line bundle. And a line bundle is in the prime variety if and only if it verifies this, assuming that the prime variety, assume at least in the case of connected case, I mean, in ramified case. Otherwise, there is two connected components, but it's not a big problem. So this condition defines the line bundles of P. Okay, so this condition, we call that this line bundle that verifies this condition anti-invariant. Okay, so we are interested in this is classical. This all the results here are very well known, but we are interested in the case of vector bundle that verifies also this isomorphism. So what we can do about higher rank? So we define a vector bundle to be anti-invariant in the same way. If the pullback by sigma is give you the dual vector bundle, okay? So if E is stable, remember the definition of stability, then E is simple in the sense that it has no, the group of automorphism of E is just C star. And so you can directly deduce that this isomorphism here is unique up to multiplication by some scalar, and so it is either symmetric or anti-symmetric by the mean that it verifies when you pull it back, you get either the transpose or minus the transpose. Okay, so primarily we have two definitions. We have anti-invariant vector bundles, which are sigma, we call them sigma symmetric. If there exists such isomorphism with a plus here, and it's called sigma alternating or anti-symmetric, if this isomorphism gives you the negative of the transpose. Okay, so primarily we have two subloci. Okay, U sigma plus XR, which is a submoduli space that parameterizes vector bundle which are sigma symmetric, and U sigma minus XR, which is the subloci that parameterizes vector bundle which are sigma alternating. All right, okay. So I should stress here that in some cases this moduli space is empty, this one here, and usually I think it's in the case of ramified. If the cover is ramified and R is odd, then there is no stable vector bundle which is sigma alternating, and this is easy to see because if there is no matrix which is anti-symmetric of rank odd, I think just from this fact from linear algebra. Okay, so if we consider this moduli space in the ramified case, then usually we assume that R is always in. Okay. All right, so I have already some results about this moduli space. We already constructed this moduli space using some GIT, geometric invariant theory, after we define what means semi-stable for them, which is a different definition. And we know already some many results about this variety, for example, dimension, the tangent space, and the smoothness, etc. Okay, we also studied the restriction of the determinant line bundle to the moduli space. It happens that when you restrict the determinant of homology line bundle to the sigma alternating moduli space, then it has a square root. It's not primitive. It give you a square root, which we call Pfaffian of homology line bundle. And but the restriction to the symmetric case is again primitive. Not that D is a primitive in the whole moduli space of vector bundles. So when you restrict it to this submoduli space, if you wish, then you get in this alternating case square root, but in the symmetric case, you just get primitive line bundle. Okay, so what can we say about strange duality for this moduli space? This is our problem. Okay, so if this strange duality were true, then we should have an isomorphism between, in one side, this vector space of global sections of the Pfaffian of cohomology line bundle on the alternating case, or maybe D here in the symmetric case, and the dual of the classical theta divisor, or the global section of the power R, or the classical theta divisor on the prime variety. Okay, so actually we have these results. It remains just one subtle case which is still resistant, but other cases are already done. So in the unramified case, everything goes very well, and these moduli spaces are isomorphic. Actually, they are isomorphic, not canonically, but there exists some isomorphism which depend on some choice of special line bundles. And the strange duality here, so the level rank duality is also true. By the mean, we have an isomorphism between the vector space of generalized theta function of level 1, the moduli space of symmetric rank R vector bundle, and the level R theta functions here on the prime variety. Note that the prime variety in this case, in the unramified case, is a principally polarized abelian variety. And the restriction of the theta divisor to P has square root. It's actually the same result as said for this vector space, this moduli space. And when you restrict the determinant bundle here, it has square root. When you restrict here the polarization from the Jacobian, it has also a square root. Okay, so this is good, and the proof depends on the study of the Hacen system on these moduli spaces. It's similar to the proof given by Bovid and Narasimhan. Okay, from these results, we can deduce the dimension of this vector space, which is equal to the dimension of this one, which can be calculated easily using classical results about abelian variety, which equals R to the power gy minus 1, where G is the genus of the base curve. Okay. So in the ramified case, let's consider the anti-invariant case. Alternating, I mean the sigma alternating case. So assume that the rank is even. Okay, first of all, that the prime variety is no longer principally polarized. So we don't have square root of the theta divisor here. So this is the first remark. Secondly, we deduce from, we get this result from the study in Hacen system that this moduli space contains 2 to the power 2n minus 1 connected components. Okay, so we should use the connected component of the identity here. Okay, so then we also get the results in this case too, after studying carefully what happens in the Hacen system. So what we get is a result similar to this one, but here you have to be careful because the rank here is 2R, but you should put just R here for the polarization of P, because here this is B is not principally polarized, so there is no longer square root here. Okay, so up to this change, I mean, we managed to prove this identity here, and I will explain the idea in the second part. Okay. So in particular, we deduce again the dimension of this vector space, which equals 2 to the power 2 to the power gy r to the power gy plus n minus 1. Okay. Okay, so I think this is the first part. If any question, because maybe I will go to more details in the second part. Okay.